In this ICFD++ example, we're going to demonstrate the laminar to turbulent flow transition tripping over an ARAM 100 wing body using the new Integral Computational Multiphysics Advanced User Interface, or ICMP AUI. Before diving into this example, I will briefly cover the new features and components of the ICFD++ AUI for the first-time user. For more in-depth understanding of the ICMP AUI features common across all Metacom software, please click on the ICMP AUI demo link popping up on the left side of the video, or refer to the ICMP AUI section of your ICFD++ documentation. This ICFD++ interface is composed of the menu bar, where the mouse is currently moving, the toolbar, which has shortcuts to the commonly used functions and visualization controls, the canvas, in which a geometry or solution is displayed, and the notebook, currently showing that you are in a CFD++ simulation setup mode. Within the notebook, ICFD++ has its action tree or setup wizard, which will guide you logically through the various steps of the problem setup, and one or more information trees, in this case the groups and boundary families tree and the boundary conditions tree. Corresponding to each item or step in the action tree is its action panel, where the user is given the relevant choices based upon choices made in previous and current panels. All panels are dockable and resizable. In this example, we'll be simulating a transonic flow over an ARAM 100 wing body configuration. A trip is introduced along the wing close to the leading edge to trip the flow over the wing's suction side from laminar to turbulent. The use of the transition tripping feature in CFD++ is demonstrated. The free stream will have an angle of attack of 2.870 degrees, a Mach number of 0.803, and a chord Reynolds number of 13.1 million. In the first step of our setup, we will be choosing the current working directory. Once this is selected, we can press OK at the bottom of the action panel to continue. Next, we are asked whether or not we want to analyze the grid files in our current working directory, as well as loading in the BC family file. We will select yes for both of these options. Once this is done, we can press OK at the bottom of this action panel. Once the grid analysis has completed, a grid information panel will pop up. This will contain information about the grid that's been analyzed and loaded. This particular grid is a 3D grid containing only hexahedral cell elements. There will be approximately 860,000 of these elements. This grid will also have 5 boundary selectors. We can then press OK at the bottom of this panel to close it. Next, we are taken to the Cell Types and Volumes action panel. Here, the hexahedral cell element type, it's already been checked for us based upon the grid analysis done in the previous step. We will make one change from the default settings in this panel. We will choose to stop for negative volumes based on total cell volume only. There are a few collapsed cells in this grid. As a result, doing a cell volume check based on the cell component volumes will terminate the run. However, the total cell volume of these collapsed cells is positive, so we can choose to use the total cell volume as our volume check. Once this is selected, we can then press OK at the bottom of this action panel to continue. Next, in the General Problem Definition action panel, this will be a general fluid problem that we'll be solving. We will not be using any preset problem class wizards, so we can leave this option as no. Then we can continue by pressing OK at the bottom of this action panel. In the CFD Problem Definition action panel, for the fluid type, we will choose gas. There will only be a single species. The flow is compressible. The type of gas will be a perfect gas. The flow speed will mostly be above Mach 0.5. The flow is viscous, and we will choose to solve the flow as turbulent, even though we'll be initializing with a very low level of turbulence at the inlet. And the simulation type will be steady state. We can press OK at the bottom of this action panel to continue. There will be no additional specifications added to this simulation, so we can keep the default no settings for all of these options and press OK at the bottom to continue. For this problem, we will choose to use the two-equation cubic k-epsilon turbulence model. We will not be defining any passive scalar, so we can keep this as no. Once this has been selected, we will press OK at the bottom to continue. We will not be applying any additional physics source terms to this problem, so we can keep this option as no and press OK. The reference quantities will be solved in dimensional mode in SI units. We can press OK at the bottom of this panel to continue. In the fluid properties panel, we will keep the default properties of air and press OK at the bottom to continue. For the initial conditions, we'll be initializing the entire domain using a temperature-based information set. We will need to create this information set, so we can press the plus button with a single left mouse click. Once a new information set has been created, we will highlight it with a single left mouse click, as well as checking it to confirm that we'll be using this particular information set. For the static pressure, we will initialize with 60,831.76 pascals, a static temperature of 255.60 Kelvin, an exit velocity of 256.9995 meters per second, a y velocity of 12.89762 meters per second, and there will be no z velocity component. For the turbulence quantities, we will initialize these at a later stage of the setup, so we can keep these at their current default settings. Once all these values have been entered, we can press OK at the bottom to continue. Before proceeding with applying the boundary conditions, I would like to go over some of the basic mouse controls of the AUI interface. With your mouse hovering the canvas, we can rotate the grid by holding down the left mouse button. We can translate by holding down the middle mouse button. We could also zoom in and out by holding down the right mouse button and moving the mouse forward and back. If we go over to the boundary families tree in the notebook, we can display and hide the grid by clicking on the grid icon adjacent to each boundary family with a single left mouse click. Now we can proceed with applying the boundary conditions to each boundary family. First, we will apply the boundary conditions to the outflow and outer boundary families. Those are boundary families number 1 and 3. We will highlight both of them. First, with a single left mouse click, we will highlight boundary family number 1, the outflow. Then, holding down the control button, we will do a single left mouse click of boundary family number 3, outer. Then we will hold down the left mouse button and drag and drop into the open boundary conditions category. An open boundary panel will pop up. Here we will choose to apply an inflow-outflow boundary condition using primitive variables. The applied condition type will be characteristics based. Here we will use the previously defined information set from the initial conditions as our information set for this boundary condition. So we will highlight this information set with a single left mouse click and check it to confirm that we will be using it. Once again, we will leave the k and epsilon values in their default states so that we can initialize them later. Once this has been applied, we can press OK to close this panel. Next, we will apply the boundary condition to the Symmetry boundary family, that's boundary family number 2. We will highlight it with a single left mouse click, and then we will hold down the left mouse button and drag and drop to the Symmetry boundary condition category. In the subsequent panel that pops up, we will choose to apply a Symmetry boundary condition and press OK to close. Next, we are going to apply the boundary conditions to the fuselage and wing boundary families. Although both of these are viscous walls, the Y plus distribution is different for each. The Y plus over the wing is approximately 0.8, and the Y plus over the fuselage is approximately 30. As a result, we will be applying a solve to wall boundary condition to the wing, but a wall function boundary condition to the fuselage. So they will each need to be a different boundary condition. First, we will highlight the fuselage boundary family with a single left mouse click. Then we will drag and drop by holding down the left mouse button into the wall boundary condition category. In the subsequent wall boundary panel that pops up, we will choose to apply a viscous wall type. For the fuselage, since the Y plus distribution is approximately 30, we will choose to use a wall function integration rather than solve to wall. The wall heat transfer type will be adiabatic, and the wall motion will be stationary with respect to mesh motion. And since there is no mesh motion, the wall will be stationary. We will not choose to apply any of the additional modifiers, so we will leave these unchecked and press OK at the bottom of this panel to confirm and close. Next, we will apply the boundary condition to the wing boundary family number 5. We will highlight this with a single left mouse click. We will hold down the left mouse button and drag and drop to the main wall boundary condition category and not the wall boundary condition used for the fuselage. We want to apply a new boundary condition to this boundary family. In the subsequent wall boundary panel that pops up, we will once again apply a viscous wall type, but the wall integration this time we will apply solve to wall rather than wall functions. We will take advantage of the fact that the Y plus distribution over the wing is less than 1. The wall heat transfer type will once again be adiabatic, and the wall motion type will be stationary with respect to mesh motion. We will also not apply any additional modifiers, so we'll leave these options unchecked, and we'll press OK at the bottom to confirm and close this panel. Now all of our boundary families should have boundary conditions applied to them. We can confirm this by looking at the boundary families tree in our notebook. You'll notice that the boundary families now all have a green check next to them. This is to confirm that a boundary condition has been applied to each. If we hover over these boundary families, we can see exactly which boundary condition has been applied to them, including the details of the boundary condition. Once we're satisfied with our settings, we can press OK at the bottom of the action panel to continue with the setup. Next, we are taken to the Turbulence Control action panel. The first thing we're going to do is change the realizability criterion from the default Schwartz to Bradshaw. We want to make sure that the flow remains laminar and doesn't switch to turbulent upstream of the trip location. The Bradshaw criterion puts more than twice the damper on eddy viscosity than the Schwartz one does, so this should help with it maintaining laminar before it reaches the trip. Next, we are going to expand the advanced model controls, and we're going to change the variable C mu formulation from the default option to the Goldberg option. For certain cases involving simple shear, the Goldberg formulation will produce a more physical result and is in fact recommended for the vast majority of flows. And finally, we are going to be adding transition tripping controls. So we will expand this section. Here we will create a new information set for the transition tripping. We will do a left mouse click of the plus sign. Once a new information set has been created, we will highlight it with a single left mouse click, as well as checking it to confirm that we will be using this information set. For this example problem, a transition trip file has already been created called trip.dat, and it should be located in the working directory of the example. The radius for the trip, in terms of marking cells to apply the source term, we will set this to 0.001 meters. And for the transition trip constant, we will enter a value of 0.0001. So that's 1e minus 4. At this point, I'm going to show what we are applying here. So the trip.dat file contains one trip line with 4 points and the XYZ location of each of these points. And this definition creates a trip line shown in this image just downstream of the leading edge of the wing. All other options in the turbulence control panel can be left in their default state. Once this is done, we can press OK at the bottom of this panel to continue with the setup. Next, we are taken to the turbulence initialization tool panel. Here we're going to initialize the turbulence for the information set applied to our initial conditions and our outer and inlet boundary conditions. We will highlight this with a single left mouse click. Then we will open up the initialization calculator with the right mouse click. For the question of is the turbulence length scale known, we will say no. As a result, we will initialize based on a turbulent to laminar viscosity ratio. The free stream turbulence level, we will enter a value of 5e minus 4. This is a very small value, so it ensures that we have a relatively laminar flow coming in. And we will enter a turbulent to laminar viscosity ratio of 0.1, once again to ensure a relatively laminar flow coming into the domain. We will then compute, which will give us the calculated K and epsilon values associated with these settings. We can press OK to close this information panel, and then we can press OK to confirm these initialized values to be entered into this information set. You should see the calculated K and epsilon values in the right side of this panel. At this point, we can press OK at the bottom of this action panel to continue with our setup. Next, we are taken to the Help Set Numerics wizard. We will choose not to use the wizard to apply our numerical settings. Instead, we will enter these manually, so we can keep these options in their default no state. We'll press OK at the bottom of this panel to continue. In the Riemann solver's numerical dissipation control panel, we will not be making any changes from the default state, so we can press OK at the bottom to continue. In the simulation strategy integration panel, we will say no to the option of is this a restart, since we will be starting from scratch. The integration type will be implicit. We will choose to run 2000 iterations, and we will try to achieve a 6-order drop in convergence. Once these settings have been applied, we will press OK to continue. Next, in the time integration control panel, we will ramp the local current number from 1 to 50. And we will do this over the first 100 steps. So 1 to 100. All other settings can be left in their default states, and we can press OK at the bottom to continue. We will leave the spatial discretization settings in their default states. The dimensionality of the polynomials has automatically been entered as 3D based on the grid analysis done at the beginning of this setup. We can press OK at the bottom to continue. Next, we're taken to the neutral plot file options panel. Here we can choose the non-primitive variables we want output to our neutral plot file, the pl2s.bin file that can be used to visualize the solution in the CFD++ visualizer. In addition to the default variable outputs, we'll want to add a couple additional turbulence outputs. So going to the turbulence pull-down menu, we will add the ratio of turbulent to laminar viscosity as an output, as well as the transition trip. This will help us identify the location of the transition trip in the visualizer by plotting it as a contour variable. Once this is done, we can press OK at the bottom of this panel to continue. In the subsequent panel, we're given the option to write to the neutral plot file's options input file. We'll leave this as checked. And we will also copy the contents of this file to the plot output options file. This will allow us to output these variables from the neutral plot file to any third-party visualization outputs. We can press OK to confirm this and close. In the probe and output files panel, we'll leave everything in their default state and press OK to continue. Next, we are taken to the save and run action panel. Here we will choose to save the input file, so we can leave this as checked, and we'll press OK. Now we have completed the setup of this example. You will now notice that the action tree has all action items with a green check next to it. This is to confirm that all parts of the setup have been completed and we are ready to run the simulation. We can run the simulation by going to the Tools pull-down menu in the menu bar and selecting Run CFD++. We will choose to run this in double precision mode using only a single CPU. In the tool runner, we can then enter Run to start the simulation. All outputs from this simulation will be written to the current working directory. For more information about post-processing and visualization, please refer to the post-processing section of this example. Thank you.